This is a recast of the 7,800-word piece, Metric Learning, from Schneepat.com. This article is about metric learning, a subfield of machine learning that focuses on developing algorithms to optimize the measurement of similarity or distance between data points. Metric learning aims to learn a distance function that captures the structure of the data and improves performance in tasks such as classification, clustering, retrieval, and recommendation systems. It has applications in computer vision, natural language processing, and other domains. Metric learning has advantages such as improved recognition performance and versatility, but also faces challenges such as the need for labeled data and the choice of suitable metrics. Various evaluation metrics, such as recall, F1 score, and AUC, are used to assess the performance of metric learning algorithms. Future directions in metric learning include addressing scalability issues and improving interpretability of learned metrics. Let's listen in.
Today we're talking about metric learning, a subfield of machine learning that focuses on developing algorithms and techniques to optimize the measurement of similarity or distance between data points. The main goal is to learn a metric or distance function that captures the inherent structure of the data and allows for effective learning and inference tasks.
That's right. Metric learning is particularly useful when dealing with data that has high-dimensional feature spaces or complex distributions. In these cases, standard distance metrics like Euclidean distance may not give satisfactory results. So, while learning a distance function adapted to the specific task or dataset, metric learning aims to improve the performance of various tasks such as classification, clustering, retrieval, and recommendation systems.
Absolutely. And what's interesting is that metric learning tackles the challenge of working with complex datasets by capturing the intrinsic geometry and relationships present in the data. Unlike traditional distance measures that assume all dimensions are equally important, metric learning algorithms can effectively reduce the impact of irrelevant or noisy data dimensions, enhance discrimination between different classes, and better distinguish between similar objects.
Right? By learning a high-quality distance metric, metric learning algorithms enable more informed decision-making processes. They can also help address the challenges of high-dimensional data analysis and improve the performance of various machine learning tasks.
Metric learning is widely applied in various fields and has numerous applications. One significant application is in computer vision. By learning a proper metric, computer vision algorithms can accurately measure and compare image dissimilarities, enabling tasks such as object recognition, image retrieval, and clustering.
That's correct. Another important application of metric learning is in recommendation systems. By learning the similarity between users and items based on their preferences, personalized recommendations can be made, enhancing user engagement and satisfaction.
Absolutely. And we can't forget about natural language processing. Metric learning plays a crucial role in tasks such as text classification, sentiment analysis, and document clustering. By learning a suitable metric, text data can be effectively compared and organized, facilitating a variety of language processing applications.
Metric learning is also widely used in computer vision tasks like face recognition and object recognition. In face recognition, metric learning can be used to learn a similarity metric that measures the similarity between face images. This improves face recognition performance. Similarly, in object recognition, metric learning can be used to measure the similarity between object images, improving object recognition accuracy.
Those are great examples. And as computer vision continues to advance and new challenges arise, the metric learning approach is likely to play an important role in addressing these challenges and further improving the performance of vision systems.
Absolutely. And to enhance the performance of metric learning algorithms, various techniques and approaches have been developed. One such technique is deep metric learning, which uses deep neural networks to learn a metric space directly from the data. It has shown promising results in applications such as face recognition, person re-identification, and image retrieval.
Another approach is the use of margin-based loss functions, which allow for better separation of classes in the learned metric space. Techniques like triplet loss and contrastive loss have been influential in this regard.
And let's not forget about ensemble learning methods. These methods combine multiple models into a single, more robust model to enhance the performance of metric learning algorithms.
Absolutely. These techniques and approaches illustrate the diverse range of strategies employed in metric learning to address the challenges of learning an effective and discriminative metric space. One approach is supervised metric learning, which utilizes labeled samples to learn a metric that can effectively discriminate between different classes. One common method is the triplet loss function, where a triplet of samples is constructed: an anchor sample, a positive sample from the same class as the anchor, and a negative sample from a different class. The objective is to learn a metric that maximizes the distance between the anchor and negative samples while minimizing the distance between the anchor and positive samples. Another popular method is the class-based loss function, where the interclass distance is maximized and the interclass distance is minimized. This is often achieved through techniques like the softmax function, which assigns higher probabilities to correct class labels.
Supervised metric learning provides a promising avenue for improving the discriminative power of distance metric learning methods. By leveraging labeled data, these techniques aim to optimize the distance or similarity measure between objects in a dataset. This can lead to better clustering, classification, and retrieval of objects in various applications, such as image recognition, recommendation systems, and information retrieval.
That's right. Metric learning is a powerful technique used in machine learning to optimize the distance or similarity measure between objects in a dataset. It learns a transformation function that maps input data into a new space, where distances between similar objects are reduced and distances between dissimilar objects are increased. This enables better clustering, classification, and retrieval of objects in various applications.
Metric learning algorithms have several advantages. First, they can improve the recognition performance of many machine learning algorithms by learning a better distance metric, reducing interclass variations, and increasing interclass separability. Second, they can be applied to various domains and tasks, such as image classification, face recognition, and information retrieval, making them highly versatile. Lastly, metric learning methods are generally easy to implement and computationally efficient, making them suitable for large-scale datasets.
However, metric learning also has its disadvantages. One major drawback is that it requires labeled training data, which can be costly and time-consuming to acquire. Additionally, choosing a suitable metric learning algorithm and parameters can be challenging, as there is no one-size-fits-all approach. Furthermore, metric learning methods may not generalize well to unseen data, leading to overfitting or performance degradation in some cases.
Absolutely. Careful consideration and evaluation are necessary when incorporating metric learning into machine learning systems. Despite these challenges, metric learning continues to be an active area of research, with ongoing efforts focused on developing more robust and efficient algorithms.
Examples and use cases of metric learning can be found in various domains such as computer vision, natural language processing, and recommendation systems. In computer vision, metric learning plays a crucial role in tasks like face recognition and image retrieval. By learning an embedding space where images of the same person are close together and images of different individuals are far apart, metric learning algorithms can improve the accuracy of these tasks.
That's right. In natural language processing, metric learning can be applied to tasks like text classification and sentiment analysis. By learning a similarity metric between documents or sentences, metric learning algorithms can enhance the performance of these tasks. And in recommendation systems, metric learning can optimize the ranking of items based on user preferences and historical data. By learning a metric that captures user preferences, recommendation systems can provide more accurate recommendations, leading to higher user satisfaction.
Metric learning is also useful in unsupervised scenarios. Unsupervised metric learning aims to discover an appropriate metric solely based on the input data, without any explicit pairwise constraints provided. One method is self-supervised metric learning, which leverages the inherent structure of the data to learn the metric. This is achieved by defining a proxy task that encourages the model to capture meaningful similarities or differences between the data points. For example, in image data, an algorithm might be trained to predict the relative position of image patches or classify transformed versions of the same image, implicitly learning a discriminative distance metric.
Unsupervised metric learning can be particularly useful in domains where obtaining pairwise constraints is challenging or in scenarios where discovering the underlying structure of the data is of interest. It allows for metric learning without relying on labeled data and provides a means to uncover patterns and relationships within datasets.
Overall, metric learning techniques and approaches provide valuable tools for optimizing distance metrics and improving the performance of machine learning algorithms. However, they also come with their own set of challenges and considerations. It's important to carefully evaluate the suitability and effectiveness of different approaches when incorporating metric learning into your own machine learning systems.
Absolutely. One of the key advantages of metric learning is its versatility and effectiveness across various domains. It has been successfully applied in computer vision, information retrieval, and natural language processing. In computer vision, metric learning algorithms have been used for tasks such as image classification, object recognition, and face verification. For example, FaceNet, a deep metric learning approach, has demonstrated state-of-the-art performance in face recognition tasks.
That's right. Metric learning has also been utilized in information retrieval to improve the performance of recommender systems and search engines. By learning and embedding space where similar items can be more easily retrieved, metric learning enhances the efficiency and accuracy of these systems. Additionally, metric learning has found applications in natural language processing, specifically in tasks such as document clustering and sentence similarity computation. This highlights the versatility of metric learning techniques across various domains.
While metric learning offers significant advantages, it's important to consider its limitations as well. One of the challenges is the reliance on labeled data. In many real-world scenarios, obtaining labeled data can be difficult and time-consuming. Metric learning also requires computational resources, as the process can be computationally expensive. Furthermore, the selection of appropriate similarity or dissimilarity measures is crucial for the quality of a learned metric, which can be challenging in some cases.
That's a great point. Another interesting aspect of metric learning is transfer learning. Transfer learning involves transferring knowledge or learned representations from one task or domain to another. In metric learning, transfer learning aims to enhance the performance of similarity metrics by leveraging knowledge from related tasks or domains. This allows for improved performance and generalization on a new task or domain with limited labeled data.
Exactly. Transfer learning and metric learning makes the techniques more robust, efficient, and effective. By leveraging the accumulated knowledge from a source task or domain, the model can avoid extensive training on new tasks and benefit from the transfer of learning. This makes metric learning techniques more applicable across various domains and scenarios.
In conclusion, metric learning is a powerful technique in machine learning that aims to find a more suitable distance metric for a given task. By learning a new metric, it becomes possible to enhance the performance of various tasks such as classification, clustering, and retrieval. The learned metric can capture the underlying similarities and dissimilarities between data points more effectively than the traditional Euclidean distance metric.
Absolutely. Metric learning offers advantages such as better feature representation, robustness to noisy and incomplete data, and efficient computation. However, it also has limitations, including the need for large amounts of labeled data, the choice of distance metric depending on prior knowledge, and assumptions about the data and scalability issues. These factors need to be carefully considered when applying metric learning to practical problems.
Examples and use cases play a crucial role in understanding the broad applicability of metric learning. For instance, in face recognition, metric learning enables accurate identification by mapping faces of the same person closer together and faces of different individuals farther apart. Metric learning is also useful in object tracking to differentiate between objects of interest and background clutter, improving tracking accuracy.
That's right. Recommender systems can benefit from metric learning by learning similarity measures between items or users, leading to more personalized recommendations. And in tasks like image retrieval and clustering, metric learning effectively groups similar images together, improving the efficiency of these tasks.
Exactly. Metric learning has several advantages in machine learning and pattern recognition. It allows for better feature representation, robustness to noisy data, and efficient computation. However, it also has limitations such as the need for labeled data, reliance on prior knowledge, and scalability issues.
Evaluation metrics are crucial in metric learning to measure the effectiveness of the learned metric. Accuracy is commonly used, but precision, recall, and F1 score provide more insights in certain scenarios. Additionally, metrics like mean average precision, area under the precision recall curve, and area under the receiver operating characteristic curve are commonly used in information retrieval and binary classification tasks to comprehensively evaluate model performance.
That's a great point. The choice of evaluation metrics should be carefully considered to accurately assess the performance of metric learning models. Before we dive into the evaluation metrics, let's quickly recap what metric learning is. Metric learning is a technique used in machine learning that aims to learn a distance metric or similarity measure for comparing objects or data points. The goal is to find a distance function that captures the inherent structure of the data in a way that is useful for a given task, such as classification or clustering.
right, and achieving both accuracy and precision is paramount in metric learning. Accuracy refers to how close a measured value is to the true value of the quantity being measured. In the context of metric learning, accuracy is the ability of a model or algorithm to correctly predict or classify a given sample. On the other hand, precision is the degree of agreement among repeated measurements of the same quantity. In metric learning, precision is related to the consistency and stability of a learned metric.
Absolutely. Accuracy and precision are critical factors because they ensure reliable and trustworthy results that can be applied in various domains such as image recognition, natural language processing, and recommender systems.
Use cases and examples of metric learning are wide-ranging, spanning various domains and fields. For example, in computer vision, metric learning has been successfully used for tasks such as face recognition, image retrieval, and object detection. Metric learning algorithms can learn a distance metric that measures face similarity, enabling accurate face identification and verification.
That's right. Metric learning techniques have also been applied to image retrieval, where they learn distance metrics that can effectively rank image similarities, facilitating efficient and precise image search. In natural language processing, metric learning has been used to learn semantic representations of words, enabling tasks such as textual similarity and clustering.
So now that we understand the importance of evaluation metrics in metric learning, let's talk about two commonly used metrics recall and F1 score. Recall measures the proportion of actual positive cases that are correctly predicted as positive by a model. It is especially important in scenarios where identifying positive cases is crucial, such as in medical diagnosis or fraud detection.
F1 score, on the other hand, is a combined metric that considers both precision and recall. It calculates the harmonic mean of precision and recall, providing a balanced evaluation of a model's performance. F1 score is particularly useful in situations where there is an imbalanced dataset or when false negatives and false positives carry equal importance.
By using both recall and F1 score, machine learning practitioners can have a comprehensive understanding of a model's predictive power and make informed decisions about its suitability for a specific task.
Absolutely. And let's not forget about the area under the curve, AUC, which is another widely used metric in evaluating the performance of metric learning algorithms. The AUC measures the performance of binary classification algorithms by calculating the area under the receiver operating characteristic, ROC curve.
The ROC curve is created by plotting the true positive rate, sensitivity, against the false positive rate, 1 minus specificity at different threshold values. The area under the curve ranges from 0 to 1, with a higher value indicating better performance. The area under the curve is preferred over accuracy when dealing with imbalanced datasets or when the costs of false positives and false negatives are different.
That's correct. AUC provides a more robust evaluation by considering all possible thresholds and their associated true positive and false positive rates. A perfect classifier would have an AUC of 1, while a random classifier would have an AUC of 0.5.
Overall, evaluation metrics play a crucial role in metric learning as they allow us to measure the effectiveness and performance of learned distance metrics. By choosing the right evaluation metrics, we can ensure that our models are reliable, trustworthy, and well-suited to their specific tasks and applications.
Absolutely. And with that, we come to the end of today's discussion on evaluation metrics in metric learning. We hope you found this topic informative and insightful.
If you have any questions or want to learn more about metric learning or evaluation metrics, please feel free to reach out to us. We're always here to help.
Now let's dive into the main points of the article. The article begins by explaining what metric learning is in the context of machine learning. Metric learning refers to the task of learning a distance metric or similarity function that accurately measures the dissimilarity or similarity between pairs of input examples. The goal is to enable a machine learning model to better understand the underlying structure of the data and make more informed decisions based on the learned distance metric.
That's right. The article goes on to explain that the distance metric can be learned using various techniques. For example, optimization algorithms can be used to minimize a distance-based loss function. Another approach is to learn a transformation of the input space that maps similar examples close to each other. Once the distance metric is learned, it can be applied to various tasks such as classification, clustering, or retrieval, where accurate measurement of similarities or dissimilarities between examples is crucial.
The article also highlights how metric learning has gained significant attention in recent years due to its potential in improving the performance of various machine learning algorithms. Traditional fixed distance metrics may fail to capture the underlying structure of the data in certain domains. Metric learning offers a solution by allowing algorithms to learn a distance metric specific to the task at hand. This has led to advancements in fields such as image recognition, face recognition, and recommendation systems.
Absolutely. The article provides some concrete examples of how metric learning has been applied in real-world scenarios. For instance, in image recognition tasks, metric learning is used to enhance the performance of convolutional neural networks, CNNs. By learning a distance metric, CNNs can better differentiate between similar-looking objects, leading to improved accuracy in image classification. Similarly, in face recognition systems, metric learning algorithms extract discriminative features from face images, enabling accurate matching and identification. Metric learning also plays a role in recommendation systems by learning the similarity metric between users or items, enabling personalized recommendations based on similarities in preferences or characteristics.
The article then discusses the challenges and future directions in metric learning. One major challenge is the scalability of metric learning algorithms to handle large-scale datasets. Current approaches often struggle to efficiently process massive amounts of data, requiring significant computational resources and time. This is an area that researchers need to address to make metric learning feasible for real-world applications.
Another challenge is the lack of a unified evaluation framework for comparing different metric learning methods. As new algorithms are being developed and proposed, it becomes crucial to have standardized benchmarks and evaluation protocols to ensure fair comparisons. This will help advance the field and enable researchers to build upon existing work.
The article also highlights the importance of interpretability in learned metrics. Understanding the underlying principles and reasoning behind the learned metric can provide valuable insights and help explain the decision-making process. This is an active research area that holds great potential for further advancements in metric learning.
In conclusion, metric learning is a technique in machine learning that aims to improve algorithm performance by learning a suitable distance metric between data points. It has been successfully applied in various domains such as image recognition, face recognition, and recommendation systems. However, there are still challenges to be addressed, including scalability, evaluation frameworks, and interpretability.
That's right. Dealing with large-scale datasets presents various challenges. The sheer volume of data requires scalable and robust infrastructures for storage and access. Additionally, processing such vast amounts of data in a timely manner requires powerful computing resources, parallel processing capabilities, and efficient algorithms.
And let's not forget about the quality and integrity of large-scale datasets. Data collection procedures, inconsistencies, and errors can affect the reliability of the data. Cleaning and curating the data to ensure accuracy becomes another challenge that researchers and practitioners have to face.
Absolutely. To overcome these challenges, researchers have proposed techniques like parallel computing, which involves dividing a large problem into smaller subproblems that can be solved simultaneously by multiple processors. This approach, along with frameworks like MapReduce, has shown significant improvements in computational time for metric learning tasks.
Distributed computing and cloud computing have also been explored to enhance the scalability and efficiency of metric learning algorithms. These techniques allow for the utilization of multiple computing resources and enable faster processing of large datasets.
Another aspect that researchers are focusing on is learning complex metrics. By employing deep learning techniques, deep neural networks can capture hierarchical and compositional relationships among data points, leading to more accurate similarity comparisons.
That's right. Deep metric learning enables the network to discover complex and discriminative patterns in the data, improving the accuracy of metric learning. Another approach is incorporating structured information, such as semantic hierarchies or ontologies, into the metric learning process. This helps capture underlying concepts and relationships among data points.
Learning complex and nonlinear metrics also poses challenges. As the number of features or dimensions increases, the amount of training data required also increases exponentially. Additionally, solving optimization problems for nonlinear metrics can be computationally expensive and time-consuming.
And let's not forget about the lack of interpretability in complex and nonlinear metrics. Understanding how the metric relates to the underlying data is crucial, especially when explaining the learned metric to domain experts or considering legal and ethical implications.
Definitely. Despite these challenges, metric learning remains a popular research area. Researchers are exploring solutions like incorporating deep learning techniques, leveraging graph-based methods, and adapting metric learning algorithms for specific tasks.
And there's still plenty of room for improvement and novel approaches in metric learning. Researchers need to continue exploring these avenues to overcome existing limitations and uncover new possibilities.
Absolutely. One of the main challenges in metric learning for multimedia data is the high dimensionality of the feature space. Images, videos, and audio data have a large number of features, making it difficult to find a suitable metric that accurately captures the similarities and differences between samples.
And obtaining labeled data for these types of data can be time-consuming and expensive. However, there are significant opportunities in metric learning for multimedia data. The availability of large-scale datasets and computational resources has opened up possibilities for developing more powerful and efficient metric learning algorithms.
That's right. Advancements in deep learning techniques such as convolutional neural networks and recurrent neural networks have shown promising results in learning expressive and discriminative representations for images, videos, and audio. These advancements contribute to the ongoing research and innovation in metric learning for multimedia data.
Absolutely. Now let's talk about the challenges and opportunities in metric learning for images, videos, and audio data. One emerging trend is the incorporation of deep learning techniques into metric learning frameworks. By leveraging deep neural networks, researchers aim to learn more discriminative representations of data, enhancing the quality of distance metrics.
Another trend involves developing more efficient and scalable approaches that can handle large-scale datasets. This includes exploring parallel computing architectures and algorithms, as well as investigating the feasibility of distributed metric learning techniques.
And there's also a growing interest in unsupervised metric learning, where the goal is to learn a distance metric without explicit pairwise supervision. This could be particularly useful when labeled data is scarce or expensive to obtain.
Absolutely. Now let's talk about another variation of metric learning called semi-supervised metric learning, SSML. This approach aims to utilize both labeled and unlabeled data for training. Since labeled data is often expensive and time-consuming to obtain, SSML leverages the availability of unlabeled data to improve the performance of metric learning algorithms.
That's right. Techniques like self-training, co-training, and self-assembling are commonly used in SSML to exploit the unlabeled data. These approaches involve iteratively updating the metric space and the labeling of unlabeled instances, ultimately learning a more discriminative and robust metric space.
However, the success of SSML relies heavily on the quality and quantity of the unlabeled data, as well as the selection and annotation of labeled data. So careful consideration needs to be given to these factors when applying SSML in practice.
Absolutely. Now let's discuss the conclusion of the article. Metric learning is a powerful technique that enables machines to learn distances suitable for specific tasks. It allows machines to understand the intricacies and complexities of high-dimensional data and facilitates more accurate and efficient decision-making processes.
Metric learning has been successfully applied in various domains such as computer vision, natural language processing, recommendation systems, and bioinformatics. Its ability to learn meaningful representations and capture the underlying structure of data has made it an indispensable tool in modern machine learning applications.
However, metric learning is still a challenging and ongoing area of research. The need for large labeled datasets, handling imbalanced data, and scalability of algorithms are some of the persistent challenges that researchers and practitioners face.
But with continuous advancements and improvements, metric learning has the potential to revolutionize various fields and industries. It can enhance similarity measurement and classification tasks, paving the way for more accurate and efficient decision-making processes.
Absolutely. The potential impact of metric learning is immense. In computer vision, it can significantly enhance object recognition, image retrieval, and image clustering tasks. In natural language processing, it can improve semantic matching models for question answering and sentiment analysis.
And in recommender systems, metric learning techniques can help understand user preferences and provide more personalized recommendations. Even in social network analysis, metric learning can aid in identifying similarities and differences between users, assisting in tasks like community detection and influence analysis.
The future of metric learning is promising. As the field continues to advance, we can expect to see even more sophisticated algorithms and models capable of handling larger datasets and extracting more nuanced similarity relationships.